Welcome everybody to our video lecture number 1, Introduction to Stats. This will be an introduction to both statistics and to our course here at the University of Cincinnati. Why do I need to learn statistics? Some of you might be asking this question, and I thought we would start there. Perhaps the simplest reason I could give you is that we learn statistics to answer interesting questions. Why people behave the way they do. Why behaviors differ across cultures. How did dinosaurs die? How businesses maximize their profits. Does eating tomatoes help you recover from cancer? Is it possible to build a quantum computer? Is the planet hotter than it used to be? In what regions? Researchers in all of these areas displayed on the screen use statistics to probe questions in these various areas. I'll pick one of these questions today to actually try to exemplify to you what is the process and when stats become useful and why. Does eating tomatoes help you recover from cancer? Well, if you're interested in this question, to answer it, you may reason based on your own observations, or you may reason based on research observations. Let's start with the first one. My father recovered from cancer. My father eats tomatoes every day. Imagine these are my observations. From these observations or premises, I can actually draw an inference and make a conclusion. Tomatoes helped my father's cancer recovery. And there is no need for stats there. Let me go up here for a second. But the question I want to ask you is, if you answer a question based on your own observations, is this the most reliable way of getting to an answer? Think about it for a second. If you think the answer is no, then try to think about why. Why is that the case? To get a chance to think about it a little bit. There are a number of reasons why reasoning based on our own observations is limiting. But in this circumstance, I want to highlight one reason. That for me to think that this conclusion is generalizable, I need to make sure that this will happen again if somebody else's father also eats tomatoes, right? If there is a relationship between recovering from cancer and eating tomatoes, this should happen over and over and over and over again, right? You know, if other people also eat tomato, do we continue to see this pattern that tomato helps? And I want to highlight something important here. If somebody tells me, let's say I made this conclusion and somebody said to me, well, but you can't be sure. And typically some people get reactive. No, I know, I've seen my father recovered from cancer and he eats so many tomatoes. It is totally possible that these two observations are true, but we have to consider the fact that my father, right, did not just eat tomatoes. He engaged in other behaviors that might have helped, including treatment, right? But it is possible that tomato did help. However, it's hard to jump to that conclusion based on a limited set of observations, right? We have to have a way to capture how generalizable those observations are, which requires broader observations, right? Not just the one you've seen right around you. So this is how, the other means of reasoning comes in. We can reason based on research observations. Of course, not every question that we come across during the day will try and find papers and find data to reason through. But I would say that when the question is important enough for you and you're going to base some very critical decision on that, it would be nice to look at data. So let's see if I can convince you by describing to you what the research process would look like here to answer this question. So you can imagine that there would be a population of all individuals initiating treatment from cancer. And then the researcher would come in and sample from this population randomly and form two different groups. To one group, the researcher would give tomatoes to eat on a daily basis, let's say, and the other group is told not to eat tomatoes at all. So you have one group eating tomatoes, the other group not eating tomatoes. And the researcher will guarantee that the two groups are similar in some other critical aspects that are already known to influence recovery, such as the type of cancer, the type of treatment they are receiving, the types of diet that they are receiving, except the tomato piece. And of course, the random sampling guarantees that the two groups are similar in other aspects that perhaps researchers don't know yet about, but that may matter for recovery. And then researchers let time go by and observe and record the recovery of the different patients. So you can think that on one side, from the group that received tomatoes, 80% recovered, and 60% only of the group that did not eat tomatoes recovered. Now, question we may be asking, or we should ask, is what can we conclude and how can we make inferences about this data? And my answer to you is that stats can help. Because really, what stats will try and tell us is whether this difference of 20% is a difference that I can trust, that will happen at a greater likelihood or probability than chance, or whether 20% is a difference that is not very likely to occur, and thus I should think that tomatoes might actually be doing something for recovery. So really what I'm saying here is that statistics is a tool that helps us determine if particular patterns we observe in research data is likely or not under particular assumptions. And the assumption here is basically that there is no difference between groups, right? There is no effect of tomatoes. If we come from the assumption that there is no effect, what's the probability that I will see a difference of 20%? Okay, so let's explore this a bit more. Does tomato help you recover from cancer? I'm saying we are reasoning based on research data. There is a research study that was very well conducted where the groups were selected randomly. They were equivalent in a number of things, except that one group ate tomatoes, the other group didn't. And we saw a difference of 20% in recovery rate, with the group that ate tomatoes recovering more than the group that did not eat tomatoes. So a difference of 20%. And we're saying that what stats will tell us is under the assumption that there is no difference, that tomatoes make no difference, right? That there is an equal number of recoveries in both populations, a population that is is undergoing treatment for cancer and is not eating tomato, and the population that's undergoing treatment for cancer, for a particular type of cancer, and is eating tomatoes. So let's assume that there is no difference. What is the probability that I would see a 20% difference in negative outcomes, right? What is that probability? If the probability is low, and you remember that in stats, there is that magic number, the probability equals to 0.05. If it's smaller than that 0.05, we say that it's low. If the probability is very low, that we see a difference of 20% if tomatoes make no difference, and we're seeing 20%, right? Then data is unlikely if tomato makes no difference. So data is evidence against the assumption that tomato makes no difference, right? That's how stats work. So I assume that tomatoes make no difference. That's the null hypothesis that I'm making there. And then stats gives me the probability that if I assume no difference, I would see the particular difference that the study is showing me. And if that probability is low, I say that my data is very unlikely if I assume that there is no difference. So I say, I'm not going to accept or reinforce the null hypothesis. There's no evidence for that null hypothesis. And then we take that as supporting the idea that tomatoes there may be something there, right? That tomato probably helps. Now, if the probability that I see a 20% difference is high, I have to assume that data is likely that what I observed would occur even if tomato made no difference, right? So that's what happens, what we conclude when that probability is greater than 0.05. Data, we basically make the conclusion that data is very likely if tomato makes no difference, right? So data is evidence for the assumption I made, which is the assumption that tomatoes make no difference. So I keep the null hypothesis. I have no grounds or no evidence to dismiss the null hypothesis, right? So I really have to keep it. So I can't even take into account or consider the possibility that tomatoes are helping the recovery, and I would not implement any changes in treatment or any public policy based on that difference that I observed, because it's way too likely, even if I assume that tomato makes no difference, right? So this is what stats does for us. It helps us determine if that particular pattern of difference that I'm seeing in data is or is not likely under the assumption of the null hypothesis, under the assumption that nothing is really going on. So let's continue. So again, stats is a tool that helps us determine if particular patterns we observe in data is or is not likely under the assumption that the null hypothesis is true, under the assumption that there is no difference in between groups that I'm observing, given the assumption there is no correlation between two variables that I'm examining, so on and so forth. Okay? So when we reason based on research observations, we'll need stats. There's no way around it, because we need stats to examine whether that pattern that we're seeing we can trust, and whether it's reliable enough for us to dismiss the null hypothesis. So statistics is really not just numbers and graphs, though graphs are pretty cool to make points and support some arguments that we make. But it is really a set of these systematic procedures that helps us extract meaning from data to answer questions based on a set of research observations. The idea is that you see this process implemented over and over again in the various classes. And I would like you to see and recognize that process, and instead of being focused on how to perform the different tests, even though you have to learn those things too, I would like you to understand, and this is my primary goal in terms of takeaway from this class, is to understand the process of using statistics to make sense of data, right? And it is that process that, regardless of the test that you will conduct, will be the same. And I hope to demonstrate that to you in the various problems that we will explore in class, right? The setting up of the null hypothesis, the looking and describing the pattern in the data, and then looking at that pattern and asking the question, is that pattern likely, enough for me to dismiss the null hypothesis, right? What is the likelihood of me seeing the data if I assume that the null hypothesis is true? Are the differences large enough for me to dismiss the null hypothesis in favor of the alternative hypothesis? Are the correlations that I'm seeing in my data strong enough for me to dismiss the null hypothesis that there is no correlation between two variables of interest? For me to dismiss the hypothesis that there is no correlation in favor of the alternative hypothesis that there is one? So this is what we'll do in this class, right? We will exercise that process to answer a variety of real-world questions. And my goal with this class is to run it in a way that you will feel comfortable with that process, and in a way that will help you with your own decision-making based on data in your professional life and also in your personal life. All right, so this is it for the introduction. I'll see you in our first lab video as well. Please watch that before trying to engage with the lab materials themselves, okay? I'll take you through how to set it up. All right, bye-bye.